Okay, yeah, perfect. Okay, cool. Hello, everyone. Thank you for joining. Today we have like the last presentation before the summer break. We have Andrew Wagenmaker with us. Andrew is a postdoc at UC Berkeley, working with Sergey Levin. Previously, he was a PhD student in computer science at University of Washington, where he was working with like Kevin Jamieson. His research focuses on like learning in dynamic interactive settings. And he's done like tons of nice work, both in like RL theory, but also like a lot of empirical papers as well. You probably know some of his papers on like robotics and everything. We're very excited to have him today. His work has been recognized by like many awards, such as like best paper nomination at Call. He's also the recipient of like some NSF fellowships. Andrew, thank you for joining us for this last presentation. Yeah, everyone, if you have questions during the presentation, as usual, feel free to raise your hand or type in the chat. And Andrew, you can start whenever you're ready.
Okay, great. Yeah, thanks for the invitation. It's fun to be back here. I've presented at the RL theory seminar uh several times when I was doing like more hardcore theory, but it's been a little bit, so I'm excited to be presenting here again. Um yeah, I can't see the chat with the way I have my monitors arranged, so if someone has questions, if someone could speak up maybe, that would probably be better, but feel free to interject at any point. Um yeah, so today I want to talk about a paper we worked on sort of in the last few months or towards the end of last year. Um, and the kind of motivation I'll be giving is in robotics, because that's kind of what I've been thinking about a lot recently. But, as I'll try to make the point, I think actually a lot of the ideas here are a lot broader. And we're really curious kind of just what people's perspective is on this. So yeah, so the title of the paper is Posterior Behavioral Cloning, and trying to think about how we should actually be doing pre-training in this era where we pre-train and then fine-tune with RL. Okay, so to kind of just like dive in, from my perspective, working on a lot of robot learning stuff the last few years, we've kind of seen this huge amount of progress, I would say, in robot learning over the last couple of years. And so the videos I'm showing you here are from various companies: Physical Intelligence, Google, Generalist. And we really, I mean, these capabilities that these companies are sort of enabling, we're seeing robots doing useful things in homes, sort of complex, dexterous manufacturing type tasks, things like that. And if we look at kind of how we got here over the last few years, it looks something like the following. So we take basically a human and they sort of operate a robot to collect a lot of data, sort of demonstrations, controlling the robot to solve some tasks they care about. Then we usually take sort of a generative model, and we train this generative model via behavioral cloning to simply predict the action that the human played in a given state. Right, and the idea here is sort of just standard behavioral cloning. So the idea here is that if we train this model properly, if we collect enough data, if we can fit this data effectively, we get a model out that can predict the action the human would play. And if the human would play an action that would lead to success, that would lead us to complete the task, then our model can also do that. Okay. Um, Okay, and so the video I'm showing you here is videos we collected. This is running Pi Zero, which is like a VLA or one of these sort of big generative models that was state of the art as of maybe about a year ago. And the task here is to pick up the spoon and set it on the plate. It's a pretty simple task. Now, what we see with this model, and what we actually often see with these models, is that, the videos I showed you on the last slide are great. This is really impressive. When you actually go to deploy these in the real world, often what happens is like sometimes it works and sometimes it doesn't. Okay, so we see in these examples, like half the time this model can pick up the spoon, and then like half the time it can't. This is actually pretty impressive in a lot of ways, that we can just take a model we download from the internet and it can like half the time work, but it's sort of not good enough still to like be deployed in like fully open world scenarios. And if you look sort of more broadly, people don't actually usually post failure videos on in their papers, because it doesn't make their method look very good. But if you dig a little bit deeper, you can find failure videos. And so sort of these are different. I think these are actually all physical intelligence models, but every robot model would have failures like this, right? Where it's sort of like dropping the espresso thing. It's not successfully completing the task. Okay. And so this paradigm that we're kind of operating in, where you sort of train a model with behavior cloning, you go and you deploy it in the real world, it gets us models that are like pretty good, but not actually good enough, right? And if we actually look at it broadly in the literature, this is a pretty ubiquitous problem in robotics right now. So you see a lot of plots like this in these sort of robot learning papers where you have a plot of x-axis is number of demonstrations, y-axis is the success rate. And the thing I want to highlight here is like we're sort of asymptoting at some value less than 100%. Like no matter how many demonstrations we collect, you never get to 100%. And these are sort of plots I pulled from a variety of papers showing something of this flavor. That like sort of this pure behavioral cloning recipe is sort of not getting us all the way to robots in the world that are like succeeding 100% of the time. And that's sort of ideally what we'd want to like reliably deploy these in the world. Okay, so how do we get past this? And there's a lot of things we might think about doing, and you know, maybe ways we could like augment our data, maybe ways we could like think about training better models, like all sorts of things we could do. The thing that I sort of am most excited about and what I've been working on a lot recently is how do we actually enable these models to improve online, right? Okay, so I deploy my model, it's sort of doing a reasonable thing, but it's not good enough. Can I then sort of use RL or sort of use this online interaction to actually have it learn and improve? And there's like 100 questions we could ask about how to do this, right? What is the best RL algorithm to use? Should I be running RL in the real world? Can I run it in a simulator, which is potentially more efficient, but you have some mismatch? Do we need to do online RL? Can I use sort of some large scale offline data? Like lots of questions. And a lot of these are questions I've thought about and I've written papers on. Um, but I think all of these questions, and really, I would say the field has primarily been focused on these sorts of questions, kind of ignores this other question that I think is actually very fundamental and for some reason like hasn't been really considered a lot. And that's actually looking at this pre-training process itself, right? So this process of taking demonstrations and distilling them into a policy, right? And so usually in robotics, what we do is we just run BC, right? We do supervised learning on these demonstrations to get a policy that predicts the demonstrations. And when we just deploy that and then we run RL on top of that, right? This process, you know, we call it pre-training of taking these demonstrations and distilling them into a model, though, is like we don't actually really usually think too much about this. We kind of just do it and it sort of works, right? So the question I want to talk about today is actually looking at this kind of pre-training phase and it's trying to understand how should we actually think about pre-training so that we have a policy that can be efficiently improved, right? If we're in this regime where the BC is not good enough, it's not getting us to 100%. We know we're going to be running RL fine tuning. Should I be doing BC in this first phase or should I be doing something else? How should I be using my demonstrations to get to a policy that's then a good initialization for RL fine tuning? Okay, so this is going to be the central question I want to talk about today. The motivation here, so I centered this around robotics, but I think for those of you like, you know, work on LLMs or other domains within AI, you'll recognize that this kind of paradigm I've just sort of outlined is actually very similar to paradigms we see in other areas of AI, right? So kind of the standard training pipeline in AI broadly, you know, beyond robotics, even to language models, so we take some big set of demonstrations. Okay, so for robots, this is humans operating robots. For language, this is just like text from the internet. We pre-train a model on it. You know, again, robots, this is BC. Language models, this is next token prediction, but next token prediction is essentially BC. And we train this model to simply fit this demonstration distribution. And then in all these domains, like the critical step is, and we go and we do RL fine tuning, right? For robotics, again, we fine tune maybe on the task we care about. For language, we do RLHF, we do RLVR, these sorts of things, right? And so sort of across AI, we've kind of like arrived at this paradigm where we take a big demonstration data set, we train a generative model on it, and we deploy this generative model in the world and we run RL fine tuning on that model, right? And then I guess the thing I want to highlight here is that if we think about the objectives, these are actually sort of two different training objectives, right? At first, we're fitting a demonstration distribution, but what we maybe want out in the end is something that maximizes some reward function, right? And so we kind of decouple these, a sort of standard AI training pipeline sort of decouples in some sense these two phases, this pre-training phase and this fine-tuning phase, and doesn't really think about sort of how should we actually be pre-training in order to fine-tune. Okay, and so while I'll be motivating this talk and sort of most of the applications I'll be talking about today on robotics, that's kind of what I've been thinking about most of the last few years. These ideas that we'll be talking about, I think, are actually a lot more general. I would actually be excited to, you know, chat with folks about how, you know, maybe in other domains these ideas might be useful. Okay, so that's kind of the setup, kind of where we're going. Does anyone have any questions on that before I sort of dive in?
So since you'll be talking about how to pre-train a policy for later improvement, like it'll probably depend on how you do the later improvement, right? So are you gonna fix some algorithm or?
Yeah, I'll answer that in a second.
Okay, cool.
We're not going to fix an algorithm, and this is actually a very good question of how to pose this problem. So the way we kind of posed it, where we don't fix an algorithm, but I would be really curious to hear if folks have thoughts on like, you know, I think there's actually a lot of flexibility in sort of formulating this problem. I think what I'll show you is kind of almost a first pass at this, but I think there's maybe more you could be done here.
Yep.
But,
okay, sounds good.
Yeah. Okay, so let me just dive in then. Okay, so the formal problem setting we're going to be looking at, very simple actually. Okay, so we want to just understand here, like theoretically, like the simplest possible setting, because it turns out we actually didn't even understand that. And so we're actually just going to look at tabular MDPs. Okay. And so the theory here, I'll go into tabular MDPs. I'll show that, towards the end how to scale these ideas to like real world robots. But for the theory part, just we're going to focus on tabular MDPs. So an MDP, it has S states, A actions, or as an H, standard tabular MDP setup. We'll assume we're given some demonstration data set. Okay, so some demonstrator. I forgot to put it on the slide, but we'll denote the demonstrator as pi beta. And we have some demonstrations collected on our environment from the demonstrator. And our end goal is that we want to find a policy pi that maximizes some reward function R. And so just notationally, we'll denote by script J pi the expected reward of policy pi. Okay, so the goal is to find a policy pi that maximizes sort of the value of J pi. Okay, so this is the standard RL setup essentially. Now we'll look at kind of the following learning procedure, basically, where we take our demonstrations and we pre-train a policy on these fully offline. And then we take this policy and with online access to the environment, we fine-tune the policy to maximize the reward. Now in this pre-training phase, we don't assume access to the environment, we don't assume access to the rewards. We're just given the demonstrations and we want to learn something from these demonstrations. This is kind of the standard BC setup. For the online phase, we're going to not assume access to demonstrations. So we're just going to assume we have this distilled policy that we then can deploy online and use this to learn through online interaction. In principle, you could, in the second phase, consider access to demonstrations as well, but in practice, people mostly don't do this, so we're kind of decoupling these phases. Okay, so just as a starting point, how in this first phase, how would we usually think about it? And the standard thing we do is just behavioral cloning. Okay, so what is behavioral cloning? It says, given this demonstration data set, just fit a policy that kind of matches the distributions of actions we observe in the data set. Okay, so at a given state, we would usually play an action essentially proportionally to the empirical probability in our data set of observing that action. In the tabular case, if we just let TH of SA and TH of S denote the total number of visits to SA and S respectively in D, this is simply saying, fit a policy to play actions proportionally to the number of times the action was played when I visited that state. Okay, so this is just sort of the empirical probabilities that we get from our data set. Okay, so this is kind of the most naive thing we do given demonstrations to train a policy. And we can actually show from this is the paper back from 2020, for the BC policy. So if you look at the value of the BC policy and you compare that to the value of the demonstrator's policy, this has suboptimality that is bounded as horizon squared times the number of states divided by the number of samples. Okay, and this is also actually known to be tight. So this paper proved a lower bound that says, in general, given these demonstrations, you can't actually do better than this rate. So the optimal rate is H squared ST.
Okay. Hold on. So here the H square is one of the H the scale of the total value, or like these are true like quadratic dependence on horizon?
Yeah, one is the scale of total value. So like we assume the rewards are at every step is in 0, 1. So the total
0, 1.
reward
Okay.
is 8.
Yeah, I just want to mention this. Like there's this. You probably noticed. I'm just bringing out for clarification. Like the Dagger papers, there was the claim that the BC suffers like quadratic dependence on horizon, but like there's some simple analysis from Dylan like recently. Like if you just view BC as like doing MLE for the whole trajectory, like you only like pay for like linear dependence.
Yeah, I think there's some like nuance in Dylan's results, right? Because it depends on like the size of the policy class and things like that. Like, I think it's like H log pi or something like this.
Okay, so yeah, I see. Like, yeah, if you're in a timing homogeneous setting, right, like maybe one of the H can be explained by log pi.
Yeah. So I think in the setting we're looking at, which is time and homogeneous, this is actually like tight, I think. But Dylan's results do show indeed that like in general, this is H squared is not necessary. but I think it depends a bit on the setting.
Okay.
Yeah. So we'll take this as a starting point, essentially, that, you know, in this sort of worst case scenario, in these tabular settings in general, in these homogeneous settings, this is the sort of optimal, right? BC essentially gets this h squared s over t scaling, and this is not in general improvable. Okay, so this says essentially, if all we care about is actually the pre-trained policy performance, and we don't actually have access to online interactions or anything like that, BC is actually sort of the best we can do. We can't actually necessarily get any more optimal behavior than this. Okay, so with this in mind, then how should we actually think about formulating this question? Like what do we actually want here? And I think this is again where, as I said just a few minutes ago, there's actually a lot of flexibility. And I actually like, you know, this is a formulation we came up with that seems, I think, a reasonable starting point. And like, as I'll show you, actually leads to practically better performance. And I think there's a lot of things we might think about here. But okay, so how did we formulate this? So I'm going to define this notion of demonstrator action coverage. And all this says is that, okay, we say a policy pi achieves demonstrator action coverage with a parameter gamma. If for all state actions, the probability that policy pi plays a given action at a given state is lower bounded by the probability that the demonstrator policy pi beta plays a given action at a given state. It's lower bounded by that probability times the scaling factor gamma. So if gamma is equal to 1, this actually essentially says pi is equal to the demonstrator policy, since it's a normalized distribution. If pi is less than 1, you know, if pi is very small, then this sort of says there's that maybe not sort of a meaningful lower bound on the actions that pi plays. If pi is, say, like not too small, then it says that pi is playing every action sort of with a probability, you know, that sort of close to the probability that pi beta plays. Okay. I'll show in a bit that this is sort of a fundamental notion, but for now I want to just define this. Okay, so we'll define this sort of demonstrator action coverage. It says pi covers the actions, it plays the actions that pi beta plays. Yeah, so I'll give an example in a second, but just, you know, to start, you can actually even see immediately from this that if we have a policy pi that does not satisfy demonstrator action coverage, then in general, sort of a lot of these RL fine-tuning algorithms actually run in practice, rejection sampling, KL regularized RL, and these sorts of things, you know, they actually cannot fine-tune pi to get it to the performance of pi beta. The reason being that usually these algorithms in some sense rely on the policy pi having the actions we need for improvement in support, right? So for rejection sampling, you sample from the base policy. For KL regularized RL, you regularize to the base policy, but when you do KL, this kind of forces you to stay in support. So if you don't actually meet demonstrator action coverage with some reasonable value of gamma, just sort of, this is almost a non-starter for some of these RL fine-tuning approaches. I'll give an example in a second, but just kind of have this in mind. Okay, so given this, how we're going to formulate this problem in terms of what we want is the following. So first off, I would like my pre-trained policy to be reasonable. Okay, so I want to, you know, I'm training this pre-trained policy on these demonstrations. I'm going to go fine-tune it with RL, but I also would maybe like this policy to itself do reasonable things. And for robotics, this is definitely the case. You know, we usually pre-train, but we actually still want that pre-trained policy to be reasonably good. And so how I'll formulate this is to say I want the pre-trained policy to be no worse than the BC policy, in the sense that the suboptimality of the pre-trained policy is upper bounded in the same way as the suboptimality of the BC policy by this h squared s over t term. Okay, so this is the first constraint I want to impose. The second constraint I want to impose is that my pre-trained policy achieves demonstrator action coverage, sort of this definition here, with the maximum possible value of gamma. And well, what does this say? It says that, you know, okay, I can't estimate my demonstrator exactly, but at least I can perhaps guarantee that I can cover the actions my demonstrator plays. If I can do that, then at least, you know, if I run an RL fine-tuning approach like rejection sampling or KL regularized RL, something that's relying on the sort of the support of the starting policy, at least in principle that algorithm could succeed. Okay, so if 2 is not met, that in principle can't necessarily succeed. So this is sort of a minimal condition.
Yeah, Andrew. So question here.
Yeah.
So why is this maximum value gamma anything other than 1?
So actually we'll see that you actually can't achieve 1 in general. So 1 would,
I guess maybe this maximum is within like what kind of constraint? It is like, so clearly you're not talking about just looking at all policies, because then I can just set like pi equals pi beta. You mean some
Yeah.
like
So okay. Well,
like minimax
basically, okay.
sense in the like learning minimax sense?
Yeah. Well, okay. I think this will become clear as I like go through the results. But basically, I guess the way to
Uh-huh.
think about it is, I will give you some. I'm going to produce some pi hat.
Uh-huh.
This is pre-trained policy. There's some unknown policy pi beta. I don't know pi beta, but it generated my demonstrations. I would like this pre-trained policy to cover the actions that pi beta plays, with high probability.
Okay.
So the kind of guarantee we're gonna go for here is actually essentially like a high probability guarantee on the satisfying this coverage guarantee at all states.
Okay.
We'll see though, you can't actually satisfy it with gamma equals 1 in general.
Okay.
Yeah, but I think that this will become clear once I start stating the results. Yeah. Okay, but so this is kind of how we're going to formulate this problem. Okay, so we want a pre-trained policy that is as good as the BC policy, so it doesn't do worse than that in terms of pre-trained performance, but then it also achieves this demonstrator action coverage. Okay, so the first question we would ask here probably is the BC policy actually itself good enough? Okay, so obviously the BC policy itself meets this constraint 1, right? Gets the suboptimality. Does the BC policy achieve some notion of demonstrator action coverage? Okay, so I want to just consider a very simple example. So let's say I have some situation like the following. I have an MDP. It has sort of two states. I start in some state S naught with probability 1 minus epsilon I transition to S2 with probability epsilon I transition to S1. Now in each of these states, the demonstrator can play one or two actions. They can either play a blue action or a green action. In the red state, they'll play with equal probability the blue action and the green action. In the yellow state, they'll just play the blue action. So this is the MDP, this is my demonstrator policy. Now, if I collect demonstrations from this policy, it might look something like the following. So for epsilon fairly small, I'm not likely to actually transition to S1 very frequently. So I probably don't have a lot of observations from S1. So while I'll have a lot of observations of the demonstrator playing the blue action in S2, I might only have a single observation from S1, and maybe it just so happens that they have not played the green action. Right? I sort of haven't observed enough samples to actually guarantee I observe that action. Okay, now if I take these demonstrations and fit a BC policy, what do I get? Well, I get something like the following, right? I haven't observed this green action, so I just don't play that. You know, when I train with BC, I simply fit the empirical distribution. In this case, the empirical distribution in the red state says only play the blue action, so I only play the blue action. Okay, so, this is kind of, simple if you think about it, but like basically you can show from this that with constant probability, unless t is large enough here being something like 1 over epsilon, you can actually end up in this situation where there is no policy in the support of my BC policy that is actually epsilon optimal. Right, so I can take a BC policy, and like in this example, we might be in a situation where the green action is actually better than the blue action. But because I only observe the blue action, I don't play the green action with my BC policy. And because of this, my policy will actually not be able to even like doesn't support an epsilon optimal behavior. Okay. So not only does it not support, is there no epsilon optimal policy in support, but the BC policy also does not allow us to identify an epsilon optimal policy, right? So if I take in this case, again, the green action is sort of the optimal action in the red state, and I roll in my BC policy an infinite number of times, I will never play the green action, right? And so because of this, I will sort of never actually observe the behavior needed for improvement, right? I will never actually observe sort of what I should have done instead, because I committed to this suboptimal blue action. Okay, and so BC essentially, you can just think of it in some sense that overfits, right? It just takes the demonstrations by fitting them empirically. It has no guarantee on its ability to capture the demonstrator's behavior, right? So, okay, going back to the criteria from the last slide, BC satisfies sort of this suboptimality guarantee, but it does not guarantee this sort of demonstrator action coverage guarantee. Okay, so BC is not sufficient for our criteria. I'll also mention though, this example is an example where demonstrator action coverage is in general necessary, right? So if the demonstrator policy plays the green action and we don't play the green action, and that green action is important, we can't guarantee that we'll actually ever match the performance of the demonstrator in RL fine tuning because we simply will not play the action we need for improvement. Okay, so this is kind of obvious, actually. Like, if you think, I don't think I'm saying anything actually super fundamental here or super like novel here. It's just saying like, look, BC is going to fit the empirical distribution. That means you might not fit all actions that the demonstrator would play. Okay, but based on the way we formulated our problem, this means that sort of the BC policy is not actually an effective starting point. Okay, so what can we do differently? Well, the first obvious thing we can do is just the following. We can just add exploration to the BC policy, right? So I think my BC policy, I just perturb it by some random noise. It's going to look something like the following. What can we say about this? Well, it turns out what you can say is something, you can say the following, which is that, okay, if you want to scale this random exploration so that I don't make my policy too suboptimal, you actually have to scale it down quite a lot, right? So this is maybe what we'd want in that when you get to state S1 here, I'm exploring the green action. I'm playing the green action, allowing me to learn and improve. In state S2, I actually would rather not play the green action. I sort of have observed a lot of samples from the blue action. I would rather just play the blue action, right? And so if I want to not increase suboptimality relative to the BC policy, it turns out that I can only explore something like this. I can only actually add a very minimal amount of exploration to the BC policy, or at this state S2, where I know what to do, my exploration will be too large and cause my suboptimality to decrease significantly, or increase significantly. And we can quantify this. So it's kind of what this theorem says, which is that for this policy, the BC policy that we're perturbing by sort of uniform exploration, if we want this policy to satisfy the suboptimality guarantee of the BC policy, then it turns out the gamma, sort of how much we can like guarantee we cover the demonstrator's actions, in this case it's green action, is quite small. And it scales at something like 1/t. So we can only actually add a very minimal amount of exploration without causing the behavior to deviate significantly. Okay. And so sort of conceptually, basically, if you look at these two options, sort of lots of exploration or sort of little exploration. In the first case, well, the issue is that we get to the state S1, we would like to explore a law because we don't really know what to do there. But if we're adding this uniform exploration, we can't explore a law. Or we're going to perturb the, we're going to cause the suboptimality to decrease too much, right? So it underexplores in some sense at the state we want to explore. If we look at this other example where we add a lot more exploration, it sort of overexplores at the state we don't want to explore, right? And so simply taking the BC policy and adding exploration, it kind of ends up in this situation where I basically cannot balance effectively the suboptimality of this policy with exploration and the coverage of actions it gets, sort of how much it actually explores the demonstrator's behavior. Okay, and so this theorem shows this kind of fundamental, right? And so kind of the takeaway from this is that if we just use BC as our starting point, if we use BC pre-training or BC pre-training plus random exploration, we simply actually can't get coverage. We can't balance this sort of our criteria. We can't efficiently minimize suboptimality of the policy while also ensuring that it achieves this demonstrator action coverage. Okay, is there any questions on that? Okay, cool. So, okay, so this basically says like the way we usually pre-train is kind of a little bit maybe insufficient. It's not quite doing the right thing. What do we actually want to do? And I want to take a slightly different perspective, maybe on demonstrators. In order to
there's a question, maybe.
Okay.
Alireza, can you just
Yeah,
speak up?
So just before continuing, I was wondering, okay, in imitation learning, we can have two objectives. One is that, okay, we can get close to the value of the expert policy, or we can literally imitate the distributions of the expert policy, distributions over the actions, right?
Yeah.
Here you're saying that, okay, we can go with the first objective and add another coverage constraint for the objective, right?
Yeah.
Is that this is, I mean, is this objective is still weaker than the imitating the distributions, or can we go for the first one?
Yeah, this is a good question. So I guess you're referring to these imitation learning approaches that instead of sort of their objective they're training for is like state distribution matching or something.
Yes, exactly.
Yeah. So this is, I would say, a weaker objective because we're not really trying to do that. I guess the two things I would say to this though. So actually the first thing, and I probably should have said this at the beginning, I think like a key motivation or a key way we're thinking about this paper was that we wanted to like have an approach that was like simple and related to what people actually do. So in practice in robotics, like these imitation learning approaches that like, you match the state distributions, like people don't actually really use these in robotics or in language models. And so kind of we're thinking more from this paradigm of like where we're just operating in roughly taking the starting point of what people actually do, which is just standard BC. So that's maybe actually the most important point here, which is that like there's other things we could do with the data, maybe like do some more state matching objective or something. but we kind of don't really want to do that because it's not really like a practical thing people do. But I guess maybe more technically, this is a different sort of objective in that we're not we're not explicitly optimizing for state matching. I think even though my guess is that even if you optimize for state matching, you still might have issues here because you can still be in this regime where the state matching objective underexplores because you haven't observed enough data, right? So you still might be in a situation where actually your demonstrator would have gone to some state if you like sort of had enough data, but you haven't observed this behavior yet. So a state matching objective won't induce going to that state, and because of that, the behavior will be suboptimal. So I think it is a stronger objective, but it probably would still have problems in this situation.
I see. Thanks.
Cool. Any other questions? Okay. So what should we do? What is the right way to think about this? So to motivate that, I want to just think about maybe a slightly different perspective on demonstrators. And I want to think about this a little bit from like sort of a Bayesian perspective. So let's assume, okay, we're in the same setting. We have some uniform prior. We assume some prior over demonstrator policies. I'll just say the uniform prior. Okay, so every demonstrator policy is equally likely. Now, given the demonstrations, we can write down a posterior distribution over demonstrator policies, right? And this essentially says, like, I observe these behaviors. What policies are most likely to be the demonstrator policy under these behaviors? This is just like Bayes' rule. There's nothing sort of sophisticated here. Within this framing, how do we think about the BC policy? Well, the BC policy is under the uniform prior, the map estimate. Okay, so usually we just think about BC as maximum likelihood estimation, but they sort of coincide if you have this uniform prior. So the BC policy is actually the policy that maximizes this posterior probability. But this kind of actually then maybe motivates something we might think about, which is like, rather than just taking the maximum of the posterior, which is what BC does, what if we actually looked at this full posterior distribution? And in particular, if we look at an example like this, and we look at this posterior distribution, what we see is a posterior distribution looks something like the following. That is, at state S2, we have a lot of samples, right? We have a lot of observations of the demonstrator playing the blue action, and so the posterior variance is actually quite small there. It's very unlikely for us, the posterior has kind of shrunk to the point where we kind of can lock in on the correct action, the blue action. At the state S1, however, the posterior distribution is actually, we only have a single sample, so the posterior variance is actually quite high. Right? We haven't fully locked in on the correct behavior, and so the posterior distribution is going to look something like the following. Right? And so essentially, BC takes this posterior and it collapses it to a single point estimate. Right? It takes all of this information we have over like our uncertainty of the demonstrator, and it just says like, here's a point estimate of their behavior. If you look at the full posterior distribution, we see that it sort of captures this notion of uncertainty of our behavior of the demonstrator at a given state. So instead of committing to the observed behavior, if we look at the posterior, it sort of puts mass on other actions, when we're not quite certain what the demonstrator would play. Okay, and this intuitively is actually maybe what we want to do here, right? We know the right behavior at S2, so we should just play that. At S1, we don't know the right behavior, so we would like to explore. And so we see in this example, the posterior distribution actually kind of precisely does that. Okay, so what can we say about this mathematically? So it turns out we can show something like the following. If we take this posterior distribution, this posterior policy, and we sort of actually have to mix it with the BC policy for reasons I can explain shortly, but if you take this posterior policy and you mix it with the BC policy, you can get a policy that has suboptimality that is bounded by sort of the suboptimality of the BC policy, h squared s over t. But we can also ensure that with high probability, the probability of the posterior, this pretraining policy plays in action the demonstrator plays is lower bounded by the demonstrator's policy divided by 1 over a plus h. It turns out we can also show that this is sort of actually roughly the optimal rate. So any demonstrator, you can show that any estimator that satisfies this pre-trained the guarantee of the BC policy, it can achieve action coverage with gamma. It must have gamma less than 1 over a. Okay, so basically up to this factor of h here, this is actually the best we can do in terms of achieving demonstrator action coverage while satisfying our suboptimality guarantee. Okay, and so what this says is essentially that this posterior policy is sort of actually optimally balancing this trade-off between exploring actions that the demonstrator might play and getting sort of good performance itself. We can't actually necessarily do better than this.
Question.
Yeah.
So a couple things. So first of all, when you said uniform prior over the policies, like, did you mean something like Dirichlet prior?
So I guess what we formulate this as In the tabular setting, it's like literally you can just write down every policy and say like the uniform any policy.
Oh, so wait. So this is a deterministic policies?
Oh man, I'm trying to remember how
Because the way I'm thinking about it is that if you think about stochastic policies, like these are pretty much just for each state you have a categorical distribution, right? So then that's not too different from like say when you do Bayesian RL like model-based learning, when you write down prior for like the tabular transition probabilities, like the canonical choice is the Dirichlet, and I don't even think like is there even a well-defined notion of uniform? I'm not sure.
Okay, so I think how I thought about this, and I would, I think I might need to review exactly how I wrote this in the paper because it's been a while since I like worked out the technical detail. But I think how I was thinking about it was that every state, every action is sort of equally likely to be played.
No, that's not a prior over the policies, right? The prior over that's a like what you described sounds like just a uniform policy, not a uniform prior over policies.
Well, but I guess like you can then like take the like product of all of these states in some sense, right? And say each of these is equally likely.
But then you have the constraint that the probability like adds up to 1 and so on.
But I guess every state decouples. So
right. So no. Yeah. I'm just looking at each state separately. Like for each state, you need to have a prior over all these distributions over actions, which is a finite set, right?
yeah. Okay, I might need to look at there might be some technicalities here. I might need to look at the paper again to see exactly what we did. I mean, okay, the intuitive way to think about it. Well, okay, so there's maybe two intuitive ways to think about this. The first is that it's sort of just saying every action is equally likely under the prior. The second way to think about it is actually not even from a Bayesian perspective at all. So intuitively, actually, what this is equivalent to is that it just is essentially measuring your uncertainty of the demonstration of the demonstrated distribution. So right at every state, you can write down a confidence interval on sort of the empirical distribution. Right, like so you have some empirical distribution. You can write down a confidence interval with high probability the demonstrated distribution lives in some set. In some sense, this is analogous. Like all of the theory that we have actually like is sort of equivalently works in that formulation too.
Yeah. So that's what I was gonna say is like this looks a lot like thinking about confidence sets, uncertainty quantification, and so on. The other thing that reminds me is and I think that there's maybe some related paper recently in the LM space that talks about how to again, like, isn't it also from Dylan, like this pre-training, like coverage principle? First, I don't exactly remember which part of that paper is particularly relevant here, but maybe one thing to say is that one thing you can think about from the more frequentist point of view is that maybe you can add some like either forward KL, reverse KL, I don't remember which is which, regularizer that maybe encourages maintaining coverage to the BC objective.
So okay, Dylan's paper is Dylan, I know the paper you're talking about from Dylan. It's a very nice paper. I think what we're doing or the regime we're operating in is actually a little bit different. So Dylan's notion actually he has this notion of like action coverage. It's actually very similar to this demonstrator action coverage.
Yep.
It's essentially the same thing. I think what they show, the main conclusion is that this actually concentrates more quickly than the like log law or like the standard BC loss. And so you could have a situation where the BC policy hasn't fully converged, but you get this action coverage. We're kind of operating and then they don't really. So theirs is more of an analysis thing. They have some interventions, but they don't really. These interventions don't like explicitly actually improve coverage in general. We're operating almost in I think a slightly different regime where it's like maybe less sort of lower sample regime than they're operating. So if you have enough samples, this is not an issue. Like if you have enough samples, you will actually just convert to a distribution that covers the demonstrator's policy. That's kind of closer to the regime they're operating in. Like they're showing that actually this does concentrate at some rate. We're kind of operating in the regime where we actually we don't have enough data for it to concentrate. So I think they're very complementary, kind of these two papers. Yeah.
And what about I guess the other thing I mentioned is that possibly using some kind of you know, either forward or whatever is called KL regularizer. That forces your distribution to cover the. I think the usual MLE or the usual KL regularizer people use is the opposite. Is like your distribution needs to stay within the demonstration distribution. But if you like change the order of the policies, like maybe you do the other way around.
Yeah, so I thought about this a little bit. You don't. I'm quite sure. I'm pretty sure you don't. And even if you do something like this, some sort of like KL regularization or entropy regularization in your problem, you don't still end up with something like this. So kind of what this says is like, it scales the uncertainty, or it scales the exploration, the coverage with your uncertainty. Naively using KL regularization or entropy regularization won't give you that. So you might end up with some sort of like okay, essentially you want to scale the exploration with your epistemic uncertainty.
Right.
The sort of standard formulation of KL and things don't in any way take into account this like notion of epistemic uncertainty.
Okay.
So you end up with something that would maybe look more like uniform exploration. Yeah. So in general, that's not going to solve the problem.
Okay.
Cool. Yeah. Okay.
Yeah, I have more questions, but I'll leave it to the end.
Okay. Actually, what is the time? Should I wrap up in like 10 minutes?
I think you aim to finish your presentation around 12, and we can have more discussion afterwards.
Okay. So yeah, I'll go into a little bit of the proof then, given that. But the kind of takeaway here is again like using this demonstrator, the posterior of the demonstrator, we can actually sort of match the performance of the BC policy while achieving almost the optimal sort of action coverage of any such policies. Okay, and so maybe the takeaway is that like rather than pre-training with BC, we should pre-train to fit this demonstrator's posterior, right? If we do that, we don't actually lose anything in terms of pre-train performance, but we gain something in terms of demonstrator coverage. Okay, I'll go very quickly through the proof. I'm not gonna have as much time as I'd hoped because I also want to leave some time at the end because we have like experimental results. So at least shows these quickly. But I'm gonna go very quickly through the proof since this is the RL theory seminar. And if I'm going to quickly, feel free to chat after on details of that. I'll save examples for the end. Okay. So how does this work? Like, why is this true? And okay, the starting point for this is if we look at this posterior policy for tabular settings, it looks something like the following. It essentially, right, the BC policy would just be TH of SA over TH of S. For the posterior policy, you basically regularize it by this extra factor of 1 and this factor of A. And if you think about it, then say you have 0 samples from a state or 1 sample out of state, this will ensure, right, if I only have 1 sample out of state, this ensures that I basically actually get the uniform distribution over actions. If I have 0 samples, it is truly the uniform distribution over actions. So this kind of regularizes me to the uniform distribution when I don't have a lot of data. Okay. So how do we show this? How do we show this suboptimality guarantee, and why is this true? So I'm going to denote this policy, the pre-train policy we use as pi tilde. So we want to bound the suboptimality of pi tilde relative to the demonstrator. So what we do is we just sort of first add and subtract the value of the BC policy, and then we can sort of upper bound this term by simply the suboptimality of the BC policy, and we're left with needing to bound the difference between the value of pi tilde and the value of the BC policy. Okay, how do we do that? Well, so we can just apply the performance difference lemma that says that for any two policies, in this case the BC policy and pi tilde, the difference in values between them is equal to the sort of difference in Q values on the distribution, state distribution induced in this case by BC. Okay, so what we see is, so we can end up with this when we can just sort of upper bound this. Okay, so now we're in a situation where the difference, sort of the suboptimality of our policy pi tilde is upper bounded by the suboptimality of the BC policy, plus this sort of how much the BC policy deviates from pi tilde on the BC policy's distribution, state distribution. Okay. Okay, so you can just upper bound these differences in Q values by the differences in actions sampled by the BC policy and pi tilde. We can look at, okay, what is the BC distribution? It's THSA over THS. The pi tilde distribution is, again, this one I showed you on the left side. And so we can then upper bound all of this, just do some algebra. You can show in the end that this is upper bounded by some value that scales as 1 over TH of S. There's some other scaling terms there, but essentially at a given state, you know, this is going to make sense. The sort of deviation between the BC distribution and pi tilde sort of decreases as TH of S increases. So you sort of have this decrease in STH of S. Okay, so because of this, we can sort of combine this, and we end up with in the situation where the suboptimality of, or the difference between the BC policy and pi tilde is upper bounded as this sort of state distribution of the BC policy, and then this term here. And we can then take this one step further. You can show on some high probability event that TH of S is going to approximately concentrate like the distribution of the base policy times the distribution, or T, the number of episodes we have, times the probability that the base policy reach that state. Because sort of the data we have here, the visit counts is sort of under the base policy pi beta. Okay, here's that kind of the key step though. So that was kind of all just set up in some sense. Here's actually the key step in the proof. So we'll do the following. So we have this term. We want to bound this term. The issue here is that this is some distribution under the BC policy, or some term under the BC policy, which is some like stochastic thing, and it's maybe not in general easy to control. The observation though is that this is some non-stochastic term now, right? This just depends on something that depends on the BC policy, or the demonstrator's policy, times the number of episodes we collected, which is just some fixed value. So what we'll do is we'll define this kind of like fake reward called the R tilde, which is simply this term, modulo some of the scaling factors. And then we see that this whole expression here is simply equal to the value of the BC policy under this sort of fake reward R tilde. Right, so we have some reward we actually care about R, and that's usually what J pi would correspond to, but we're saying, okay, look at the value of this other reward R tilde. Now, the kind of nice thing about BC is it's actually agnostic to what the reward is, right? So it doesn't actually matter. BC doesn't actually involve the reward, and so these guarantees on BC simply scale for any reward function, as long as they're sort of bounded nicely and such, right? And so because of that, we can actually take this term, and we can upper bound the value using the standard BC guarantees. We can upper bound the sort of fake reward the BC policy collects by the fake reward pi beta collects, plus some scaling factor here, right? Now, the key thing here is it allows us to switch, in this case, instead of being under this distribution pi hat BC, which is hard to control, we've now switched to this distribution pi beta, which is actually very nice. Because if you look now at sort of our expression, we have this this corresponds roughly to the amount of visitations from pi beta, i.e. the uncertainty at a given state that would be induced by playing pi beta. And now we actually get that, we get the state distribution here is also pi beta. Okay, so then you can take this and you can upper bound it, and what we see is we can sort of get these to cancel, and you end up with this nice expression that scales like sort of roughly what we would maybe hope, H of S over T. Okay, the intuition here then in some sense is that by using sort of this property of BC to switch distributions, we can kind of perfectly match our uncertainty with how much we would visit a state. Right, and so this says essentially that, you know, if there's a large deviation, this is sort of the deviation between the BC policy and the posterior policy at a given state. If that deviation is large, or that deviation will only be large if pi beta is unlikely to visit that state, right? So if pi beta, if this is a large value, pi beta is likely to visit that state, then the deviation will be small, because we'll sort of have visited this state enough to actually learn the demonstrator's behavior. If the deviation is large, that means we're unlikely to visit the state. And so we might have states where we don't actually know the demonstrator's behavior, and as such, the posterior policy deviates significantly from the true policy, the demonstrator's policy, or the BC policy. But in some sense, it doesn't matter, because we're scaling that contribution by this low probability, right? By the probability that pi beta visits that state, which is small. And so we can kind of get this perfect matching where the uncertainty sort of only affects states where we're unlikely to visit, where the BC policy is unlikely to be correct. In that states where we are likely to visit, where the BC policy is likely to be correct, we actually don't induce very much deviation from the BC policy. Okay, so what you can end up with then is, again, we wanted to bound this difference between the BC policy and pi tilde, and you can sort of bound it in the end by this term here. There's some scaling factor alpha you have to play with, but if you choose alpha right, something like 1 over H plus A, you get the guarantee we want in the end. Okay, but the takeaway here sort of intuitively is that going back to an example like this, if we add exploration, if we add deviation from the BC policy at a state where we don't really know what to do, where we haven't observed a lot of samples, it doesn't increase suboptimality because the BC policy might not be correct there anyways. In the posterior, this posterior policy sort of perfectly balances how much exploration we add with how uncertain we are actually about the behavior. Okay, I know that was very quick. I'm gonna just keep going though because I have some other stuff I want to discuss in terms of like implementing this and getting it to work in practice. But happy to chat about the proof more in the Q&A. Okay, also I'm gonna skip the proof sketch for the lower bound too, in the interest of time. Okay, so how do we actually make this work? Okay, so this is sort of nice theoretically. Now, we've limited ourselves theoretically to tabular MDPs. It's obviously not reflective of the real world. How do we think about then scaling this to the real world setting? And my primary focus these days is working in robotics. So I really wanted to understand how to make this work on real robots. And to motivate this, I want to just think about a very simple setting. So let's say our demonstrator is a Gaussian policy. Okay, so they're parameterized by some mean and some variance. And we have some samples from this Gaussian policy. Now, if you can write down just explicitly here in closed form what the demonstrator's posterior is, and in this case, the demonstrator's posterior is simply equal to, well, here, I'll show you the BC. The BC policy in this case, well, precisely actually the map estimate, is equal to essentially the empirical observations of the action times with some scaling. Okay, we assume actually in this case the mean is unknown, but the variance is known. Okay, so this is the BC policy. If we look at what the demonstrator's posterior is, we see it's the BC policy plus some extra noise term, right? That, again, takes into account, in some sense, our uncertainty. Okay, so this is gonna be a bit roundabout, but you'll see in the end like why this is important. Okay, so what we want to do is I want to come up with a generic way to generate samples for my posterior policy, because if I can do that, then I can maybe scale this to like real robots. Okay, so how do we think about doing that? So the first thing we show is that you can solve some optimization problem over your data, over your observations, and if you perturb sort of the value of data you fit. Okay, so I want to fit an estimate of the mean of my demonstrator, but I'm going to perturb the actions by some random noise. And if I do that and I solve this optimization, it turns out that the solution to this optimization, this perturbed optimization, is a sample from my posterior. Okay, this result, or very similar results, have been in the literature for a long time. I think I first saw this Ian Osmond, some early Ian Osmond work, but I think it's been used in various other papers. So the point is just simply that in this Gaussian setting, you can get a sample from your posterior distribution simply by solving an optimization problem. You don't need to actually write down explicitly what this distribution is. In a Gaussian setting, I don't actually really care about this, but this is very nice because as we'll see, this allows us to scale. Okay. So what do we do then to generate a sample from the posterior? Okay, we can do the following. So we first compute the BC policy. We know how to do that. We just fit a BC policy. Then we're going to compute a bunch of policies that sort of are by solving the perturbed optimization problem that I showed you. And these policies then generate samples, are essentially samples from my posterior distribution. Then what I can do is I can look at the variance in the predictions of these samples from my posterior distribution. And because these are samples from this distribution, if I look at the variance in those predictions, the variance will scale as the true variance I care about here, right? In particular, like this term. So then what I can do in the end is I can take a sample from my BC policy, and I can take a sample from my posterior distribution, I can take a sample from a normal distribution, which is variance distributed, variance scaling as the ensemble variance, and I can set my actual action A hat to the BC action plus this perturbation. And you can show them that in this case, this action will actually be sampled from the posterior. Okay, this is quite roundabout. In general, for Gaussians, you wouldn't want to do this, but the nice thing is everything I've written down here, you can easily scale to like general function approximation settings. Okay, so the algorithm we actually do is the following. We take the demonstration data set, we generate sort of perturbed variants of this, and we train an ensemble of policies, BC policies, on these perturbed variants of it. Okay, and this is just standard BC. We just use like L2 regression. You then take this ensemble and you look at the variance of the ensemble and you return that. Okay. again, in the Gaussian case, this would actually be exact. In the general case, it's not, but you can still run this. And then given these sort of variance, this is covariance estimated from your ensemble, we're going to train another policy where we take the state and actions from the true data set, we perturb these actions by the variance of our ensemble at that given state, and we train another policy that sort of models not just the state actions in the data set, but the state and actions perturbed by this variance. Okay. So I guess conceptually what this is doing is it's using these ensemble-based methods to estimate uncertainty at a state in the data set. And then it's training another policy that is sort of perturbing the samples from the data set by the uncertainty. In the Gaussian case, this is actually precisely a sample from the posterior. In general, it's sort of something like reasonable-ish. For those familiar with any of these ensemble-based methods in deep RL, like DQN, these sorts of things, this is conceptually similar, more in the BC case though. But like sort of what we're doing is actually very analogous. And I think actually maybe the key thing here, and maybe what for me was kind of most exciting, is this only requires BC, right? So this estimating that this covariance, the uncertainty, simply requires training k BC policies. BC is very scalable. We know we can do this. And then fitting this final policy is again just BC. It's just on a noisy objective. You run BC on a noisy objective. Okay, so the point is you can actually instantiate this sort of posterior thing by just running BC. You just might have to run it more times than you normally would, but it's still just BC. That means you can actually run this in practice. So I'm just going to go very quickly through the results. Basically, it works. So our performance is in blue. I'm showing you here the RL fine-tuning performance. Maybe I'll just show this one. So on the left, we actually have the pre-trained performance of BC versus our policy. You can see they're quite similar, which is what our theory says. But if you look at the fine-tuned performance, BC, it's very hard to improve in this case. Well, our policy, you can much more easily improve. This also works in practice, so we ran this on a robot. What I'm showing you here is rollouts of the BC policy. And kind of what I want to highlight here is that if you look at rolling out the pre-train policy, if you look at the pre-train performance, the pre-train behavior, it actually looks very similar, right? So the goal here is to pick up this corn and set it in the pot. Both of them are mostly failing, but there's sort of not obvious differences. They kind of both just like mostly fail. What's interesting though is if you look at the fine-tuning performance, it's very hard to fine-tune the BC policy with RL here. It kind of gets stuck. It doesn't like have an expressive enough distribution. But if you look at the demonstrator's posterior, what we're proposing, you can actually much more easily fine-tune this with RL. Okay, and so sort of more quantitatively, you can see this where again, in the real world, the pre-train performance is pretty similar for our policy versus BC, but the fine-tuned performance for our policy is significantly better. Okay, and so this actually then works. Like we actually see real improvements in practice pre-training with this kind of posterior rather than pre-training with the BC policy, where we match the BC policy's pre-trained performance, so we don't lose anything relative to BC, but we actually do gain meaningful expressivity in terms of our ability to fine-tune. Okay, so just to wrap up, I just want to say maybe the takeaway from this is just like, maybe the first takeaway is that we should think about not just training with BC, pre-training with BC, but we should pre-train to fit the demonstrator's posterior. Maybe the high-level takeaway is like, in these sort of modern AI systems where we're doing these kind of decoupled objectives, it actually pays to think about, how we can better integrate these objectives. Like if we don't just fully decouple the stages, we actually think about scalable ways to couple them, we can actually do better and get sort of meaningful real-world improvements. Okay, so thank you all for listening. This is joint work with Sergey, Chelsea, Raymond, and Perry. And yeah, happy to take any questions.
Nice.
Yeah,
Thanks
I
for
guess
the
we should just speak up if you have a question.
Alec, do you want to start?
So sorry, I just don't know. I just raised it by mistake. I'm just trying to unraise it. Okay, I apologize.
Oh, okay.
Chava, go ahead.
Hey, Andre. Hey, guys. Very nice piece of work. Regarding this empirical part, I wonder how big the ensemble was.
Yeah, so that's like a hyperparameter you tune.
Yeah.
It ranges in size from like 10 to like 100.
Right.
Some settings seem more sensitive than others. I think for like the real world experiment, we did like an ensemble of 10, if I recall. But I'd have to double check what we say in the paper. But it was in the range 10 to 100. I think past that point, you don't see improvements.
Oh, yeah, I wanted to ask for the low number is because computational limitations or whatnot.
Yeah, I mean, I guess in some cases it was just like you didn't see improvements past 10.
Right.
Some cases you did though. Obviously, yeah, if you have to train on 100, I mean, I think okay. The limitation of this approach is it does involve more training time. So, it's only supervised learning, which is nice, but like you still have to train a lot of policies. So if you're in a setting where you have a lot of data or a really big policy, you kind of still want to minimize this. That wasn't an issue for us in particular because the data sizes and policy sizes we ran the experiments on weren't like prohibitive. But if you try to use that scale, that could be, you probably want to reduce the ensemble size as much as possible.
And some more details about the translation of the ensemble method to neural networks. You had two terms. One was the label some perturbations, and the other term was just the weights, like the initial weights, and like the. Yeah, I'm not. Yeah, okay. So maybe on this one, on this slide, that is actually the answer to my question. I was wondering whether you were regularizing towards the initial weights as well when training these ensembles, or
So what we do in the end, I guess. Sorry if I understand your question correctly. We have this. Okay, so you first fit the covariance. Which
I'm asking a question about that. How do you do that?
Oh, how do you do this?
Yeah.
Okay, so what we actually do is you do bootstrap subsamples of your data. So you take your data set, you sample with replacement from it, and you train a policy on that. And then you just look at the predictions of this policy at each state. In practice, we actually just fit deterministic MLPs. So you're just doing true regression.
Right.
And that seems to work pretty well.
Yeah. Yeah. So whatever was on the previous slide, which was the more principled way of producing samples from the posterior, is not actually being used.
Okay. Yeah. So this is a good point. So the principled way to do it for Gaussian cases is you perturb the action by a Gaussian random variable.
And you're also regularizing towards around the
yeah, you also have this regularization too. We did try the perturbing with noise. It doesn't work as well in practice. We never explicitly did this sort of regularization towards this N01 actually. It could be interesting to try. I suspect in practice it wouldn't matter a lot, but it could be interesting to look at actually.
Yeah, if we go back to the algorithm that you actually use in practice, so know that you're just running regression on noisy data. I guess you don't want to train with too many perturbations for too long, because then the regression method might be filtering out the noise that you're adding, right?
Well, so actually when you it actually shouldn't either. So in our case, when we do the bootstrapped sampling, if you think about it, the reason that you have variance in your predictions of your network, if you do this bootstrap sampling thing, is that you have a state where some of the networks observed action A and some of them didn't, right? So the networks that observed SA in the data set will predict A at S. That networks that didn't observe SA won't predict A. And so if a sample SA is super common in the data set, then sort of all of them will observe it and all of them will have predictions that match. If it's not common, they'll have variance of prediction. So you can actually train these for as long as you want. And you still will have them.
I guess the point is that you're adding noise to the actions only once.
Only once,
and exactly. You're training to that, so that noise is not going to be filtered out.
Right. That is super important. Yeah. You have to do it like that.
Okay. Yeah. Good. Yeah. Thanks.
Yeah, I guess I also have I have to run like in 5 minutes, but so there are some questions I had when I hear the talk. So first, just to clarify the nature of your theoretical results, are those like Bayesian results that where the guarantee also assume like the prior, or like the results themselves are frequentist?
No, it's not a Bayesian result.
Okay, so this is like
It's truly a frequentist
Bayesian
result. Like the
I see.
Bayesian thing was truly just for expositional purposes.
Yeah, got it. That's what I
Yeah.
guessed. So related to that, I guess just conceptually trying to understand what is happening. Like maybe one way, the one picture I'm depicting in my mind when you introduce the algorithm is like, okay, so generally you can do when you do behavior cloning, you can form a version space, like think about like all possible policies that fit with the data, right? And then maybe you say, okay, find one single policy that sort of gives you the best worst case coverage over all of them, something of that sort. Oh,
yeah.
okay.
Yeah, conceptually that's exactly right. Like I think the difference is like, okay, when you usually do BC, you just pick a single hypothesis in your hypothesis class.
Right.
This is sort of saying like, no, you should actually consider the full hypothesis class and like which ones you
Yeah,
can eliminate.
yeah. I guess the sort of like, if I think of that way, it looks very familiar, in terms of how we think, in online RL, offline RL, whenever there's need for.
Yeah, exactly. No, I mean, like a lot of conceptually, this is taking a lot of the stuff we know to be like correct from RL, and it's just saying you should also do that for BC.
Yeah. Okay, cool. Okay, sorry, I have to run a little earlier today, but this is like a really cool talk. I guess Antoine can handle the rest of the.
Yeah.
Okay. Yeah.
Thank you.
Nice chatting.
Yeah. Thanks, Nan. Bye. Are there other questions?
Yeah, I had a question, but I had it more on the kind of empirical results what you were doing, and I had a couple, but I don't want to hog up the. I'm sure somebody else would want to ask something. But I was kind of curious about. So if I understood kind of the paper correctly, or sort of what you were describing correctly. You kind of like make this policy to kind of compensate for the fact that the BC over focuses on like demonstration data, and hence like it kind of fails towards the like when you have to do the actual tasks. And so I was wondering, because a lot of my research right now revolves around like long horizon problems, like why the models don't succeed at long horizon tasks. And I was kind of thinking, like sometimes when I read the papers, I find that kind of the hidden line is that a lot of like the potential problem can be is that it's not like the action coverage for like a single state, but like if the policy itself that has been pre-trained like visits the right like sequence of uncertain states without like going off distribution too much, if it makes sense. And so I was kind of thinking, like, you were talking about like the posterior and uncertainty, and I was wondering if you have this posterior kind of uncertainty, does it still like remain useful as like kind of the horizon increases, or like does the uncertainty cause more error, like it compounds and it kind of goes into this like bad state distribution?
Yeah.
No,
that's a really good question. I think it's a pretty subtle point, actually. So the first thing I will say is like our theoretical guarantees show that the performance should be no different than the BC policy. And that's also what we observe in practice. So again, like here's just from sort of a lot of different, these results are average over a lot of different environments. We see the pre-trained performance is identical. So I think because of that, it seems that when you do this kind of like posterior thing, you end up in a situation where you do actually indeed match the pre-train performance. So if the pre-train policy succeeds half the time, you should as well. Like the way it adds the noise doesn't cause you to deviate from that. Now,
Right.
the other flip side of this, though, is that like when we add the noise, we are adding it at an action, at a state level, right? So you're saying perturb the action distribution every state by a certain amount. What that means is that you might have situations where that does lead to distribution shift, right? Like if you do this very early on, you might perturb yourself to a state where you fail or you don't know what to do, and the BC policy is really bad. So I think the way we balance it, like the way that we actually do the perturbations to scale them with our uncertainty, seems to fix this.
Okay.
Like you don't seem to actually, this doesn't seem to be an issue, but like you could imagine maybe you want to do, rather than just like action state level perturbations, you want to do like trajectory level perturbations in some way. And the challenge there is like, it's not obvious how to actually realize that in practice, but
Yeah.
I think so. I think, yeah, we haven't observed what you're describing to be an issue because of the way we scale the exploration, but there might be better things we could think about doing here.
Okay, that makes sense. Thank you. Yeah. And then I had just maybe a small follow-up, and then I guess you kind of already addressed it, but I was wondering because I was thinking about like the your approach kind of works around the demonstrators action. But then I was thinking that sometimes you get like data sets, like if the data sets are large enough, especially you get like demonstration is actually not comes out to the good quality potentially, or it's like suboptimal.
Yeah.
And I was wondering if you kind of the approach preserves too much of that like bad behavior, or like kind of it escapes it with diversity somehow. But I mean, like what you said about scaling makes sense to me. But yeah, if you kind of like had any thoughts about like what to do with these like kind of poor kind of demonstrations coming in and kind of messing it up, like
yeah. So I mean, I think in general, like how to filter demonstrations is like a very important problem, although it's a little bit orthogonal. I mean, I think we're kind of operating here in the regime where like, yeah, you're just given demonstrations, you fit something on them, but you want to do RL fine tuning. Or like, this is not like, we're operating in a regime where we assume the BC policy, what we get out is not going to be like perfect. And we want to do some fine tuning. So yeah, like in practice, I think for robotics, at least in practice, what we often have is like, we have a lot of demonstrations that are all successful. Like they all complete the task. They might do it in different ways and at different rates and with different reliability and all these sorts of things. So it's hard to filter that then, because it's like they're all getting positive reward in some sense, but you're still like the distribution you're trying to fit there is very complex, and we don't get a perfect policy for fitting that. So I guess conceptually that's maybe what I think of as like kind of the setting we're operating in, because I think that is like very kind of the real world setting we care about, where we maybe have correct demonstrations, but they're very diverse and they're very hard to fit. And so you need to do some amount of fine tuning on top of it. But yeah, more generally, how to filter demonstrations correctly, it's definitely a very, I think, open problem, and a lot of work still needs to be done, probably.
Okay, thank you so much. Thank you.
Yep, sure.
I have two short clarification questions. The first clarification question is that the demonstrator posterior, when you're training it in the practical experiments, it's just like a Gaussian policy, and then you're maximizing likelihood. Is that what you do?
So in the practical experiments, we
like in this part,
this part we just train regression.
Yeah, sure. I got it.
Like this part, we're using a diffusion policy.
It's a diffusion policy. Okay.
Yeah.
So it needs to model somehow the distribution, right? That's the point.
Yeah, you need to be able to model, like, I guess in some sense, it's like a complex mixture of Gaussian. So the noise we add when we fit this is Gaussian, but you're trying to model this like complex distribution of mixture.
And have you tried just like a Gaussian policy class?
I haven't tried. I suspect
that would be the obvious.
Yeah, like I think mostly in like robot learning today, people use diffusion policies. Like they usually just perform, even in normal BC, they perform a lot better than Gaussian policies. So I never tried it for that reason. Like in principle, it might work because you are still fitting a Gaussian in some sense.
Yeah.
But usually diffusion policies just tend to work better.
Right, but in this case, it's the data seems to be just coming from Gaussians. It's like there is no reason to believe that it's multimodal or anything like that. But I don't know.
Yeah, like in principle, I think this might be true, but I think in practice, usually diffusion policies still do better.
Okay. Wow.
Yeah.
Okay. Whatever. Yeah.
It would be
Okay.
worth trying, but I'm pretty sure it would do
Yeah.
worse than diffusion policies.
And then okay, got it. First part, just the regression thing. So that looks like that you are trying to fit a posterior, but the prior is a Dirac at 0 in a way, right? Like it's and you say that like it doesn't matter, like kind of a weird prior, right? Like there's no prior here.
Yeah, I guess so. This
It's
going
just
back
like
to your
it
comment
fits
of
in
like
stereo.
you should really have this regularization term.
Yeah, I really wonder why that doesn't matter. It's like
this is a good question. Honestly, I didn't try this.
Yeah.
It could improve performance.
Yeah.
I will say the way you instantiate the posterior does matter. So like we did what we did in the end was these like bootstrap samples of the data. When we were trying, the other thing you can try is the thing motivated by the Gaussian case, where you add noise to the actions, and that works a lot worse. So the way you instantiate this algorithm actually matters a lot for this algorithm. It probably actually would have been worth. We probably should have tried the like regularization thing to the prior. I just didn't think about it when I was writing the code, but it would be interesting to look into.
Okay. All right. Okay. Just small clarification questions. Thanks. Cool.
Cool. Maybe let me start the recording here.